Welcome to This Explainer. Look, today we're moving way beyond just treating AI like some mysterious black box, and we're going to dive deep into the actual architecture of semantic search. We live in this crazy world where everyone's using tools like ChatGPT, and enterprise search platforms are seemingly reading our minds. But honestly, very few people understand what's actually happening under the hood. So if you've ever wondered how large language models truly understand the intent behind your words and somehow pull the absolute perfect document out of millions in just a fraction of a second, well, you are in the exact right place. We're going to completely demystify the core technology that makes all of this modern magic possible. Okay, let's kick things off by looking at a massive headache for traditional keyword search. Human language is, well, it's incredibly messy, and the way we type is almost never consistent. Just think about these two simple phrases. My payment didn't go through, and transaction was declined. To you and me, these describe the exact same frustrating problem, right? We inherently know they're identical concepts, but a standard keyword search, it relies strictly on matching characters. So it looks at these two concepts and sees them as completely unrelated, because they literally don't share a single word in common. The actual meaning gets entirely lost in the mechanics of the alphabet, and for decades, this fragile system was the absolute bottleneck of information retrieval. To solve this vocabulary mismatch, we basically have to build a bridge, because the reality is, text is discrete, but math is continuous. When we speak or write, we're using discrete tokens, individual words that are rigidly defined. But meaning is fluid. It's got all these nuances, shades, and connections. So we need to transition from the rigid, discrete symbols of human text into the continuous, sliding landscape of mathematics, where relationships can actually be measured. Honestly, every single time you ask an AI to find similar documents, recommend a product, or compare meanings, you are actively relying on this exact mathematical bridge. So here is our game plan for today. We're going to follow the exact journey of a query, starting with a vocabulary mismatch, then enter the embedding, check out measuring similarity, discuss the art of chunking, and wrap up with searching at scale. Starting with Section 1, the vocabulary mismatch, and why keyword search isn't enough. Let's ground this in a real-world scenario. Imagine you're managing a database of, say, 10,000 customer support tickets. If you try to find a systemic issue and rely totally on exact keywords, you're going to miss the vast majority of your relevant data. Why? Because out of those 10,000 tickets, people are going to use dozens, if not hundreds, of wildly different ways to say the exact same thing. Typos, slang, completely weird phrasing, all of it just bypasses your keyword rules. We absolutely need a system that understands the true intent behind the ticket, not just the random characters typed on the keyboard. Which brings us nicely to Section 2. Enter the embedding, where meaning becomes geometry. Let's introduce the absolute hero of our story here, the mechanism that finally lets computers understand context. I want you to think of an embedding as a massive, multidimensional map. It takes a human sentence and translates it into a dense vector, which is basically just a giant coordinate list of hundreds or thousands of floating point numbers. Now, why does this matter? Because in this mathematical space, geometric proximity actually encodes semantic similarity. When a model maps out language, it pushes similar concepts physically close together in that space, while unrelated concepts get shoved far apart. So king and queen live in the exact same neighborhood, but Apple the fruit and Apple the tech company, they might start out miles apart depending on the context. You never read these numbers, you just measure the physical distance between them. The history of this tech is actually wild, and it's moved incredibly fast. Back in 2013, Google's Word2Vec completely blew people's minds by proving that vector arithmetic could capture meaning. Like, they showed that if you took the geometric coordinates for king, subtracted man, and added woman, you landed exactly on the coordinates for queen. I mean, it was a total revelation. Then by 2018, transformer models changed the game again by introducing special tokens to summarize the context of whole inputs, not just isolated words. In 2019, SentenceBERT brought in contrastive learning, actively rewarding models for pushing similar pairs of text closer together. And right up to modern 2026 instruction-tuned models, we can now use task prefixes to tell the AI exactly what kind of embedding we want. Like, hey, I'm answering a question, or I'm clustering data, or I'm retrieving a document. But it wasn't always smooth sailing. Early methods had a pretty fatal flaw. Before these modern contextual techniques, systems would often just average out the individual word vectors in a sentence to get a single overall coordinate. Think about these two phrases, dog bites man and man bites dog. If you just average the math of those three words, you're giving these two vastly different sentences the exact same mathematical representation. You've completely lost the word order, and worse, you've lost the subject and the object. Context changes everything.
which is exactly why modern models don't just look at words, they look at how those words interact with each other. That leads us right into section 3, measuring similarity and the rules of the vector realm. Because once our text is translated and securely placed into this dense vector space, we need rules to measure exactly how close these concepts are to one another.
When you're measuring similarity in this space, you generally have 3 main metrics: cosine similarity, dot product, and Euclidean distance. Now, the huge takeaway here is that cosine similarity is going to be your default for about 90% of retrieval tasks. Instead of measuring the sheer physical distance between 2 points, it actually measures the angle between their vectors. And this is absolutely crucial because it completely ignores magnitude. Think about it. If a user types a tiny 5-word query and the perfect answer is buried in a massive 500-word document, a standard Euclidean distance would say they're super far apart just because of the massive size difference. But cosine similarity? It recognizes that they are pointing in the exact same semantic direction, effectively linking your tiny query straight to that long answer.
Moving to section 4, the art of chunking and breaking down large documents. Listen, you literally cannot embed a 50-page PDF as a single vector. If you try to force an entire manual into one coordinate, the meaning just becomes this washed-out average of dozens of completely different topics, and mathematically, it ends up being similar to absolutely nothing.
Your chunking strategy can literally make or break your entire retrieval system. If you use a basic fixed-size chunk, you might blindly tell the system to cut the text every 50 words. Well, that means you might arbitrarily cut a sentence right in the middle of a word, like literally slicing declined in half. You completely destroy the thought, and the resulting vector is just useless garbage. Alternatively, using a sentence-based chunking strategy ensures the cut happens cleanly at a period, preserving the complete, uncorrupted semantic meaning of the thought before it ever gets mapped into geometry.
Depending on your data, you've got a few options here to balance cost and quality. Fixed size is super simple to code, but incredibly risky for meaning. Sentence-based is fantastic if you've got clean articles. Then you have recursive chunking, which is brilliant because it tries to break things down by paragraphs first, then sentences, making it adapt beautifully to mixed formatting, like Markdown. And finally, there's semantic chunking. This is where you actually use a smaller AI model to identify exactly where the topic shifts in the text, and you make your cuts right there. It definitely costs more compute power upfront, but man, it delivers the absolute highest retrieval quality down the line. In practice, most production systems find a sweet spot right around 256 to 512 tokens per chunk, usually with a slight overlap so absolutely no context is lost at the edges.
And finally, section 5, searching at scale, going from math to production. Everything we've discussed works flawlessly when you're just testing things out in a sandbox on your laptop, but taking this into a live, breathing production environment brings us to the climax of our pipeline journey. Because here's the big reality check. How do you actually search 1 million vectors in real time? Let's say a user hits enter on their search bar. If you have to compare their single query against every single document in your database to find that perfect cosine similarity match, the computational weight becomes an immediate, crippling bottleneck. To put that into perspective, if you try to do a brute force search over just 1 million high-dimensional vectors, you are looking at roughly 1.5 billion multiply-add operations per single query. It is a staggering amount of math. Your server latency would absolutely crash. It would literally take seconds to return a single search result, which, let's be honest, in the modern AI world is an unforgivable eternity. So this is exactly where approximate nearest neighbor algorithms step in to save the day, with HNSW being the gold standard right now. Instead of scanning a flat list, the algorithm pre-builds a multi-layer graph. Think of it kind of like zooming in on a Maps app. First, it searches the sparse top layers, the zoomed-out view, to quickly find the general semantic neighborhood of the query. Then it greedily descends into the denser, zoomed-in bottom layers to find the exact closest neighbors. Sure, it doesn't guarantee the absolute perfect mathematical match, but it is 99% accurate, and it turns an impossible sequential scan into a lightning-fast graph traversal, giving you results in single-digit milliseconds. And to optimize the pipeline even further, modern architectures are starting to adopt something called Matryoshka embeddings. Just like those Russian nesting dolls they're named after, these models are deliberately trained so that the most vital core semantic features are front-loaded into the very first dimensions of the vector. Since the most important math is right at the beginning, you can literally slice off the end of a vector, trunking it from a heavy 1,536 dimensions down to just 256. You slash your storage footprint and your processing time massively while keeping the vector completely functional with almost zero drop in retrieval accuracy. It's awesome.
Now, for maximum precision at enterprise scale, production systems use a really powerful retrieve then re-rank pattern. First, they deploy blazing fast BI encoders. These act like a giant wide net, quickly searching the database independently to grab the top 100 possible candidate documents. Then, they hand those 100 candidates over to cross-encoders. Now, cross-encoders act like a magnifying glass. They're way slower, but highly accurate because they process the user's query and the document simultaneously, deeply observing how the words interact with each other. They perfectly re-rank those 100 candidates to finalize the flawless top 10 results. And hey, if storage and memory are your absolute worst enemies, binary quantization is going to be your best friend. This is a technique that shrinks vector sizes by converting memory-heavy floating point numbers into single bits, just ones and zeros. So, a massive 6,000 byte vector suddenly becomes less than 200 bytes. This unlocks an astonishing 32x reduction in memory usage. It means you can hold millions of documents entirely in RAM for hyper-fast retrieval, or even run sophisticated semantic search locally, right on an edge device like a smartphone. As we wrap up this explainer, I really want you to consider the massive implications of everything we've just unpacked. You now know exactly how we build the bridge between human text and continuous mathematics. You know how to chunk it, how to map it, and how to scale it for production. But if meaning is truly just geometry, what happens to our underlying architecture when we start mapping the complex shapes of entirely new languages, massive interconnected code bases, or even abstract multimodal human thoughts? The tools are entirely in your hands now. What new worlds will you map in vector space? Thanks for joining me on this deep dive. Let's keep building.